Haroun, so let's get a bit of speaker background here. And Paul. Oh, this will take twice.
Both of us, yeah. It's both of us.
Yes. So Haroun, what's your sort of discipline?
Well, I'm recently mostly in UK on carbon capture storage. My main interest is in the transportation issues. That's pipeline primarily, but also more lately shipping, which is becoming more and more important. I think, everybody is now considering the two together, and there are advantages and disadvantages with both. And it seems likely that we are going towards transportation by both options for different clusters. So
how did a sort of a transport person come to get involved with steel, apart from ripping it up? Yeah.
No, that's a good question. Whenever you look at the any technology which is related to capture, there is, of course, the question of the purity of the CO2. And you can't just do your capture design and optimization without knowing what's going to happen further downstream, because you capture the CO2, it has to go down through the pipeline. And then if you don't meet the specification of the pipeline in terms of purities, then you'll have problems. So there needs to be communication. So almost a majority of the projects that have the EU projects, which are related to CCS, many of them involve element of CO2 transportation and storage for this very same reason. You can't do one in isolation of the other. So that's how I got involved.
Okay.
And I'm learning more about capture. I'm definitely not an expert. So this is why I've got Paul here, who is going to carry the can, as they say. So when it comes to the capture, he's the one who knows more about the capture aspects of this project. As I'll explain, there is quite a lot, many different aspects to this project. Capture is a center point, but there are all the other aspects that we also need to look at.
Yes.
Complete the picture. Paul, do you want to say?
Yeah, sure. How did you get into steel, Haroun? It's because you met me.
Actually,
where are you? Yeah. Are you in Sweden? Or
yeah, right. I'm based in northern Sweden. But when I met Haroun, which was
is that why it's dark? Is that why it's dark? Because it's so far north. No, you've just got your curtains pulled. Okay.
Yeah, that's right. It's although it's almost summer now. Well, I mean, it's 4 degrees outside, but it's almost summer, so there'll be 100% light for the next 100 days or so.
Yeah, I mean, if it's 4 degrees, it's probably warmer than here actually, but it's been very cold. Yeah. And then, how did you come to move to Sweden? You're not Swedish, are you?
Well, actually, I was yes, I was born in the UK, but I'm actually a Dutch citizen now. I worked for more than 20 years in the Netherlands on catalytic processes involving hydrogen and CO2, and also started developing one of the part of the technology we're talking about today. And I've taken that from, say, a 2-gram scale in the lab all the way up to 20 tons of material for CO2 capture. And I think the reason that we're here today, together with Haroun, is because we met each other probably about 6 years ago, and at a conference that was mainly talking about transport issues. And we realized that there was this disconnect between the people doing development of CO2 capture technologies and the wishes of people wanting to transport CO2 in pipelines, etc. And that's basically where this this collaboration came about.
Okay, and can I just ask, well, I suppose we'll hear about it, but presumably in terms of the process, you've been patenting it and getting general IP protection throughout, so.
Yeah, that's right. So when one of the technologies was developed, then there were some patents brought out by Air Products back in 1999.
Right.
And we worked in the beginning with Air Products, but they changed their business model and drifted away. But in the meantime, we developed so many new things that we started patenting ourselves. And so if you look at there's two technology lines within this project, and one is basically patented by TNO in the Netherlands, although it was ECN at the time. There's 5 or 6 patents all about improvements to the process. And the other was patented by CSIC, Carlos Abernades in Spain, for the other technology. So there are, and each of the technologies, the good thing about this project is that we're bringing both of them together. We see an integration in the steel plant where you can use both of them. And typically a steel plant has so many different sources of CO2. It's difficult to imagine how you can use one technology to capture them all. But in C4U, we've managed to capture the majority of the emissions with just 2 technologies by looking at, you know, interesting ways of putting them together.
Very good. Okay. All right. Well, thanks for the background. I think the numbers doubled while we were talking. That's amazing. I think that's one of the quickest sort of accretions I've seen. So who's going first, gentlemen?
I lead on, and then
okay, the floor's yours.
Chip in. He knows where to switch. Thank you. Good afternoon, everyone, and thank you for inviting us to this series of presentations. The title of today's presentation is Advanced Carbon Capture for Steel Industries Integrated in CCUS Clusters. It's basically an EC funded project. It's in response to one of the Horizon 2020 calls in 2020. We started just over a year ago. It's a 4-year project. It's led by us, University College London, with a budget of around 13.8545 million euros. We also have a contribution from China, which is separately funded to involving collaboration with the Chinese partners that I'll talk about more later. It is, in terms of diversity, is a very unique project because we have a very diverse mix of partners with different expertise. So we bring together social scientists, engineers, technology developers, equipment manufacturers, business developers, and industry stakeholders. In fact, you had to have such a composition of different expertise and disciplines to be able to successfully respond to the call because of its nature, because it really was a very diverse call, which involved all of these different disciplines. In total, we have 22 partners.
Haroun?
Yes.
Sorry to interrupt. Is your presentation supposed to be showing at the moment?
Yes.
I thought maybe it was supposed to be there.
I thought it was doing what all the politicians do, which is don't put anything in writing. You were just talking to us.
I'm glad you said. Okay, so here we go. 22 partners. Here is a list of the different partners. 9 from Europe. We've got also a partner in China, in Canada, and also the US. So moving on. C4U, the challenge. Why is this capturing CO2 in the steel industry is important? Well, I hope when I finish reading these four bullet points, you'll see the reason. First is that the iron and steel industry represents the largest energy consuming manufacturing sector in the world, with average specific emissions being 1.83 tons of CO2 per ton of steel. It's remarkable. You produce more CO2 than every ton of steel. So almost up to 1.5 to 1.8 times as much. 1.8 gigatons of CO2 were emitted in 2018 from the iron and steel industry. up by 4.6% compared to 2017, accounting for up to 8% of anthropogenic CO2 emissions. That is a huge amount when you think about the total. So it has been widely recognized that reducing CO2 emissions from the iron and steel industry, making industry is considered to be as one of the 5 pillars in meeting the net zero emission target. You have to reduce the CO2 emissions from the steel industry in order to be able to have a realistic chance of hitting the net zero targets by 2050 or 2030, depending on which country you're dealing with. So it's a question of not putting all your eggs in one basket. You need to pursue, like the COVID, you can't just rely on one vaccine. So you need a range, and much the same goes with the with capturing CO2 from the steel industry. You got to pursue different promising capture technologies in order to capture CO2 from the steel industry. And you, at the same time, you need to make sure that it is, of course, at minimum cost and energy efficient, whilst also taking on board very much the social economic barriers. So main objectives, as Paul said at the beginning, we have 2 promising capture technologies that have shown quite a bit of promise. And these are both solid-based. We'll hear more about them later. We need to raise these to a high TRL level. They are called DISPLACE and CASOH capture technologies. We need to analyze the environmental and business impacts for the integration of these 2 technologies at large scale in the ArcelorMittal plant in Ghent as part of the North Sea Port Industrial Cluster. So this is where we are focusing on. This is the industrial cluster. We have several industrial emitters. The main one being the ArcelorMittal plant in Ghent. And this is where we would like to integrate our capture technologies to this plant. As part of this industrial cluster, we need to also develop a dynamic flow model for the monitoring and control and optimal safe operation of the cluster network, taking into account the CO2 quality impact on the transportation and storage infrastructure. So you will not just, it's not a standalone situation. We are just considering capture and transport from A to B. We are working in the context of an industrial cluster. So we are using our North Sea Port Industrial Cluster as the main focus of our attention. We need to test and develop approaches with stakeholders and end users to assess advanced readiness for societal readiness for CCUS in industrial clusters. It was one of the main requirements of the call. And if you look at many of the calls which are coming up for an CCS, you've got to have that on board, because if you don't have society on board, then you have problems. And disseminate, like many other projects, disseminate and exploit the project results. Now, what is our ambition? In combination, the 2 C4U capture technologies aim to capture up to 90% of the total emissions from the steel plant. So this diagram here basically shows where are the various sources of CO2 coming from in a steel making plant. We have majority of the CO2, which is emitted from the blast furnace operations. Then we have the sinter plant, basic oxygen. So as you can see, this is a distribution of the different places in the steel plant where the CO2 is emitted. What is unique with our 2 technologies is that together, these 2 technologies will capture up to 90%. So the majority of these CO2 emissions that are emitted, which have different heat values, different compositions, different specifications. With the 2 C4U capture technologies, we hope to capture up to 90% of these, and therefore have a major impact on reducing the CO2 emissions from the steel industry. Now, let's look at this in perspective. This is a very useful plot which was produced. It's a part of the steel roadmap. It shows, I'm going to spend a couple of minutes explaining the significance of this. Basically, the y-axis here shows the CO2 intensity. That's ton of CO2 produced per ton of steel. Okay, so from 0 up to 1.6 tons per ton, spanning from 1990 up to 2050, approximately 60 years time span. And these are different trends according to different hypotheses. The pink dotted line is the way that the CO2 reductions CO2 has to be capped in accordance to European emission standards. So the CO2 which is emitted from the steel industry has to follow this trend by 2050. So there needs to be approximately 80 or 90% reduction in the CO2 emissions in accordance to the European Commission. Now, the black curve here basically shows business as usual. So basically, if we don't do anything and continue things, the CO2 emissions as they were up from 2010 onwards. So we will have this situation where we would have only a marginal reduction in the CO2 reductions. The blue curve here shows the maximum CO2 reduction in an economic way. So what you can do is you can modify your steel plant, make it more efficient in order to, through different advanced technologies, in order to hit this point here, where you'll have 15% reduction in the CO2 emissions and yet remain economical. You can do more, make further changes in your steel plant without CCS and reach up to 40% reduction in the CO2 emissions. But the problem is that you'll be losing money. So the steel plant won't be operating economically and it may go out of business. This line here, line 4, shows what can be achieved with CCS. So if we have CCS on board, then we'll hit this target here by 2050. We'll reach 50%. Still not good enough. We've got a way to go to hit the what is being stipulated by the European Commission in terms of emission caps. So to do that, we need breakthrough technologies to hit this point. So this is what we need to go from point 4 to point 5. And this is the aim of the C4U capture technologies, to be able to capture that much extra CO2. And that's equivalent to 823 megatons of CO2 by 2050 through the deployment of breakthrough capture technologies. Hopefully it will be such as those which is developed through the C4U project. So a quick one, this is the usual pair diagram to give you a brief snapshot of what the different work packages involve. Work package 1 and work package 2, the work on elevating the TRL level for the 2 capture technologies, DISPLACE and CASOH. You'll hear about those more later. In the next work package, we integrate these CO2 capture technologies that we've demonstrated into the steel plant and also in an industrial cluster. Our main focus is the North Seaport Industrial Cluster. And of course, we need to consider societal readiness, public policy, and business case. So societal readiness and public policy, what needs to be done to make sure that we have public on our side. That's work package 5. And of course, we need to have appropriate business models to entice business, different models to make sure that to try and make this the CCUS clusters commercially viable through the development of different business models. And like many of these projects such as this, we need to effectively disseminate and communicate our project results, and work package 8 involves the project management. I'll now move over to pass to Paul Cobden, where he can talk about the two capture technologies, and I'll take over from him after. Over to you, Paul.
Thanks, Haroun. Could you stop sharing the screen and then I can share the screen?
Yeah.
Thank you. Okay, so I'm going to cover work packages 1 to 3 very quickly. First, just to talk about what the pilots are and where the demonstration is and where this came from. If you know me and Carlos Abernades from CSIC, we've been working on CO2 capture technologies since the early 2000s. And in CSIC, they've been working on calcium looping post-combustion capture. And I've been working on pre-combustion capture with the sorption enhanced water gas shift. Now, we worked together before the C4U project in a different project called Ascent. And C4U is basically what's happened because of that project. And in that project, we actually switched roles. And so we started to look at using calcium looping for pre-combustion capture and the CWAX technology for post-combustion capture. So C4U is atypical, but C4U is good atypical. If we look at where we're going to be performing these demonstrations, the idea here is because we're asking for high TRL demonstration in the call. And so we have to be associated with large scale facilities. So in Asturias at the ArcelorMittal plant, we'll be building the CASOH technology, which uses calcium copper as the base material. 4,000 kilometers away, which is where I am, and this is the current temperature profile. So it's quite good today, but it can go up to 1 degree per 100 kilometers in the middle of winter when it gets down to -30 here, and it's still 10 degrees C in Asturias. Today it's 3 degrees in Lulio, and there we're developing the DISPLACE technology. And if you just see here, this is where I hope you can see my pointer. This is where the blast furnace is, and you see this little line. This is a 2 meter wide diameter pipe taking the blast furnace gas from the blast furnace there, and we have a small port in there taking around about 1,000 normal cubic meters an hour of blast furnace gas to the demonstration site. And the reason I talked about the temperature gradient is because I think our two technologies are also very much defined by a temperature gradient. In the CASOH process, we're talking about up to 1 degree C per millimeter, and in the hydrotelsite process, it can be more like 1 degree C per centimeter. Of course, a very different scale than the weather phenomena. So the status of our pilot preparations is we started just over a year ago, and both of the pilots have similar activities. So they're all both going to show more than 2,000 hours of demonstration at high TRL. And most of the activities of this year are still on engineering, procurement, construction, etc. Both of the technologies have already delivered on their basis of design. So where special attention was paid for equipment delivery, getting everything in on time, the mass balances, the operational philosophy of the pilot, and all of the responsibilities. Unlike some research projects, because we're aiming at a very high TRL level, that means we can't afford to let anything go wrong. when we program for a campaign, that means we have to have up to 40 people running around, running the campaign, doing 24/7 work. And we can't have the possibility that some material is not delivered and therefore that everything will be still. So a lot of extra work compared to, say, a typical research project, where if you don't get a material, you can do something else, and you're not relying on tens of other people to run the project. It works in a different way. So if I now go on to specifically the two pilots separately, work package 1 is DISPLACE oven process for reheating ovens. So it's interesting first to understand what a reheating oven is. This is a typical reheating oven. This is in Poland at the ArcelorMittal plant, 2.4 million tons a year, a walking beam furnace. This is, when the steel is cast, it's very hot, but in fact, before you can roll the steel, you need to let it cool down and then reheat it again to get a good temperature profile through your metal. And so this is done in reheating ovens. It's only about 2 or 3% of the CO2 output of the steel plant, but it's one of those sources that needs to be thought about how to decarbonize that. And it can be done in 2 ways. You can decarbonize a gas that you would burn going into the oven, or you could decarbonize the burnt gas with the CO2. So both pre and post combustion options are actually going to be looked at in this project. Here are 2 very much smaller furnaces, which are going to do the 2 1,000-hour campaigns. On the left-hand side, you've got something called a chamber furnace, and which typically has 800 kilo samples in it. And on the right-hand side, you've got a walking beam furnace, which can process up to 3 tons an hour of steel. And the 2 campaigns are one in which we use the technology to first decarbonize the CO2, so pre-combustion, and the nitrogen hydrogen is used in oxy-combustion in the furnace for heating the metal. On the right-hand side, in the walking beam furnace, we'll take the blast furnace gas directly, do oxy-combustion on it, and then remove the CO2. The heart of the process is the technology as shown here. This is the pilot as it already exists today, water gas shift catalyst, which is important for nitrogen hydrogen campaign. And we've got this 10-meter column, which is about 60 centimeter diameter. It contains about up to 3 tons of material, and that can be used for the CO2 capture, both from the nitrogen, the blast furnace gas directly, and also from the combusted blast furnace gas. So what does the process look like at its heart? This is just for the post-combustion capture. So there's oxy-combustion of blast furnace gas in the reheating process, leading to a stream which is led across an adsorption bed at 400 degrees C. Once the hydrotal site has absorbed the CO2, then the bed is regenerated. The bed is regenerated with steam, but this is steam at 400 degrees C. The trick here is because there's blocks of CO2 and steam moving through the bed, you actually can reuse some of the steam. So when you regenerate the bed, you push out a block of steam first, which is used to displace the CO2 in another part of the cycle. And so there's only a relatively small amount of steam needed to run this cycle, even though the actual amount of steam seems quite large. Because you're reusing the steam, you can really bring down the energy need for the total of the CO2 capture. Now onto work package 2, that's the calcium assisted steel mill off-gas hydrogen process. This is very much a pre-combustion process. At the moment, the plans are here for producing the pilot. There's already a lot of things in place, the connection for the blast furnace gas to the technology. The plot has been sorted out. The pilot, the control rooms have been built, and now the full design of the reactors is taking place. Here you see typically the kind of cycle that we're running in the CASOH process is actually a 3-step process. There's the production of a fuel. So blast furnace gas enters into the bed. Capture of CO2 from the blast furnace gas occurs along with the water gas shift reaction. So no CO or CO2 leaves the bed, so you produce a nitrogen hydrogen mix. Then, because you've got this copper material in the bed, you can oxidize that, which is also a heat removal step. But the oxidation of copper is very mild, so your temperature doesn't increase that much, such that the calcium carbonate is decomposed. And then you can use a fuel which supplies more, which supplies also hydrogen, and the hydrogen reduction of the copper oxide back to copper actually provides all the heat for regeneration of the CO2. And of course, included in this, there's various ways of managing the heat between the different cycles, and all that heat can actually be integrated well within a steel plant. So it's a 3-step cycle in essence. The main drivers for the pilot design is that we had to build a single pack bed, a high TRL, which means that the system will have round about 0.3 megawatts of hydrogen LHV it's making, and about 0.7 megawatts of thermal energy from the heat regeneration. And of course, the idea is to keep within budget, which I think is really going to happen. If we look at the initial layout, I think we can go through this quite quickly, but main points here were to avoid high temperature valves and limit the operation temperature to 10 atmospheres. And one of the first deliverables was a common design practice, and this is what I alluded to before. This is about making sure that everybody understands what their role is within the project. A much more detailed plan than you'd ever find in a project proposal. And this is exactly because working at such a big scale, you can't take chances in not having something delivered, because then there's too many people that have no work to do or have to do other work. And that's a really important point. I'd just like to show you the reactor as is. It's 5 meters high. The internal diameter is around about 0.5 meters. It's filled with calcium oxide and copper active materials provided by CASOH and Johnson Matthey. And already these materials have been tested within the facilities that already exist. And so it's very well known exactly what's going to go into the packed bed reactors. Now, I want to very quickly talk about work package 3, which is the integration of CO2 capture plant technologies in the steel plant. And this is very much at the heart of why C4U is such a good idea. If we look at a steel plant can have really up to 30 different types of CO2 streams coming out of it. Some are much bigger than others, for example, the blast furnace or the basic oxygen furnace and the coke furnace. But by a clever integration, and this is just a bit of a Mickey Mouse diagram, we can actually use the move around all the gases in the steel plant to capture up to 90%. And so part of work package 3 aims and objectives is to really look at the an optimal energy and cost integration of the two different technologies between in the steel plant. And so one final sheet before we move back to Haroun is what kind of synergies are there between the two different technologies. Now, the CASOH technology can be used to process the coke oven gas, the basic oxygen furnace gas, the blast furnace gas, and to produce a nitrogen and hydrogen as a fuel. But these fuels can be used in both the hot stoves and the reheating furnace. But also, when the CASOH technology looks at the blast furnace gas, because there's so much nitrogen in the blast furnace gas, it's very difficult to really get a pure CO2. And the DISPLACE technology can be put downstream the CASOH to upgrade the CO2. And of course, the DISPLACE technology can be used in all types of oxidative media. And with that, I'd very much like to switch back to Haroun.
Okay, thank you, Paul. Over to me. I need to, a bit anxious of time, so I need to, if everybody please forgive me if I go too faster. Hopefully we'll have some time for questions.
Yeah, don't worry, Haroun, we often spill over.
Okay, very good, thank you.
Do your best, but don't worry too much.
I do my best. Thank you, Paul, again for the. I definitely could have never done such a good job as you did. So I'm glad that you took over on the description of the capture technologies. Now, moving on to the next step, we've integrated the. We wish to integrate the capture technology into the steel plant. The next is in the context of an industrial cluster. So we want to integrate the integrated capture unit into an industrial cluster, and work package 4 deals with that. So let's put things into perspective. At 60 megatons per annum, the industrial activities of the 3 industrial port areas of Ghent, Antwerp, and Rotterdam account for up to 1/3 of the total CO2 emissions of Belgium and the Netherlands combined. Clustering of these 3 regions with a common CO2 transportation infrastructure will allow the geological storage of up to 10 million tons of CO2 per annum in depleted gas fields in the Dutch coast, making it one of the largest CCUS clusters of its kind in the world. Now, Work Package 4 aims and objectives: to develop a multi-source dynamic flow model along with realistic scale experimentation for the optimal control and operation of the North Sea Port Industrial Cluster, taking into account the impact of the CO2 quality on the associated pipeline transportation and storage safety, and also investigate the utilization opportunities, employ the CO2 capture cost models developed in Work Package 3, along with agent-based models to assess capture, energy, and cost penalties for the North Sea Port Cluster for 2030 and 2050 decarbonisation scenarios. We appreciate that if you need to design, look into the future when you are designing such clusters to make sure that you have sufficient capacity and also are able to deal with the change in the landscape as far as the replacement of displacement of some of the emission technologies with more renewable technologies is concerned. There may be changes in the amount of reductions in the total amount of CO2 which may be permitted from each one of the emitters. So you need to think ahead and consider these scenarios. So we are also looking at the situation of how things will look in 2050 in the design of our and operation of our cluster. And of course, we need to look at the environmental impact of the North Sea Port CCS cluster using life cycle analysis. Our main focus of attention, as I mentioned, is the North Sea Port Industrial Cluster. The ArcelorMittal plant is shown here near Ghent. As you can see, there are several different emission sources along this path. Ultimately, there are plans to connect all these to a common pipeline network infrastructure for transport further up into the port of Notre Dame, and also ultimately for storage offshore. The range, as you can see, the range of different emitters are quite diverse. We have fertilizer plants, starch manufacturing, renewable plastics, titanium dioxide production, power plants, the list goes on. So several very diverse, different amounts of CO2 that they produce. This is based on data that we were able to obtain in 2017. And as you see, their focus in the CO2 project, in the C4U project, is the ArcelorMittal plant in Ghent, which is the highest emitter at 4.11 tons, million tons per year. Now, the monitoring and optimal control of such a complex network presents several challenges. Some emission sources may have relatively low purity CO2 and low flow rate. Other emission sources may have relatively high CO2 purity and high flow rate. There will also be likely temporal variations in the feed flow rate. So you can imagine a situation when you have a source which is continuously emitting CO2 into the network because of its nature of operation. You can have other sources which may dispose more CO2 during daytime as compared to nighttime. Other problem is that the impurities that may be tolerated in the pipeline may not be tolerated in the storage site. So, and on top it all, a relatively stable flow of constant purity CO2 is required at the injection site. So you have several challenges. Where do you draw the line? You've got an emitter which is producing low quality CO2 at high flow rate, and another one doing the opposite. What kind of purity specification can you impose on them so that you have basically a balanced flow through the main trunk line of the CO2, meeting the storage specification? And to be able to do that, you need to understand exactly what goes on in terms of the purity and the flows in the entire network. And this is where we come in work package 4. We are developing a multi-source flow model where we can basically simulate exactly what goes on at any point, at any time throughout this pipeline network infrastructure as a function of different CO2 impurities and different flow rates. So if we simulate this, we can understand what goes on. We can track the CO2 composition at any point, at any time throughout the network. And based on that capability, then we have an effective control role where we can monitor and control the entire system so that we can stipulate the type of, the degree of purification that we require from each one of these emitters, taking into account how the emission rate changes with time, and also the flow rate as well as the purity. So the ultimate aim is to have that kind of capability for understanding the dynamics of the flow in the model. Now, one of the main aspects of this work is basically experimentation. Safety is a major issue. If, for example, you have a rupture of the pipeline, you need to basically see what the dispersion behavior of the CO2 is. During flow also, are you going to end up with multi-phase flow or single-phase flow, depending on the depending on the CO2 specification. You cannot predict these theoretically without the confidence of having experiments to back up the theory. So part of our project here is the utilization of a pipeline that we developed through a previous FP7 project in collaboration with China. It's the largest experimental test pipeline in the world for conducting CO2 release experiments, 250 meters long, heavily instrumented, so we can find out exactly what the temperature and pressure variations are along the length of the pipeline. We pressurize it with CO2 with different types of impurities that we are likely to encounter. We rupture it and we look at the flow behavior. So these are the two diagrams. This is a, we can do both puncture experiments where we can control, basically simulate a puncture in the pipeline as well as a full bore rupture. I'm going to show you a brief aerial video of the system that the pipeline that we constructed in China. It speaks for itself. So this is the entire length of the pipeline. We have temperature and pressure monitors along the length of the pipeline throughout. This is the point of release. Pressurized with the pipeline with different CO2 compositions. We can do both rupture and puncture experiments. Measure the concentration of the CO2 plume as a function of distance. Find out if you have two-phase flow taking place along the length of the pipeline, and also work out safe distances from the pipeline, depending on the particular pressure and temperature and the composition that we are likely to encounter. Work package 5, societal readiness and public policy aims and objectives, led by Radboud University in collaboration with Element Energy and CEPS. We generate public support for CCUS through identifying concerns through informed dialogue, constructing narratives that address public concerns, increase the feasibility of large-scale CCUS clusters through identifying policy options that address public concerns, and analyze policy options that address public concerns. As I said, many of these projects have failed because of poor public consultation. If you don't have public on your side, society on your side, then you run into problems. So throughout the C4U project, it is a major work package where we look at the societal aspects. The methodology, collecting data through reviewing literature and through interviews and focus groups, address the rollout of CCUS in the transition towards the Paris goal by building on the notion of just transition and analyzing policy instruments used and considered in various EU countries such as Belgium, Netherlands, UK, Sweden, and Spain. Long-term business models, very important. You never make a profit by having CCS. So we need to make sure that at least you have appropriate business models to make it viable. So we have Element Energy, who have extensive experience in doing this kind of work in the UK with considerable success. We have them on board, basically. They look at the enabling the deployment of the North Sea Port Industrial Cluster by developing novel and investable long-term business models. And the business models are broadly transferable, so it's not just that it will be applicable to a cluster in Europe, it will be applicable. The aim is to make these generic so that they will become applicable and transferable to different clusters across the world. And so these are the different elements: desk research on CCS risks and challenges, identification of learnings from the UK progress and projects. UK has made tremendous progress in the context of industrial clusters. So there is a lot that Europe can learn from it. Stakeholder analysis and engagement, very important aspects. Business model innovation, framework design, and scenario analysis, and then finally business model shortlisting and development. And here is the methodology from the commencement of the project until its termination. where we end up with recommendations on long-term business models and appropriate for the North Seaport CCUS industrial cluster. Dissemination through knowledge sharing and public engagement. This involves everyone in the project, which is led by climate strategies, aims and objectives, ongoing its activity throughout the project, and ensures that the project results are exploited to the full extent and disseminated to relevant stakeholders to facilitate the large-scale rollout of CCUS. I will skip to the next slide here, basically, which captures the previous one. So this is the breakdown of our dissemination activities. We have, first thing that we had to do is to develop what's called the dissemination and exploitation of results, the PEDR document. It's a live document that we constantly update and embodies basically the different activities that we will take place in terms of the dissemination of the project results. The first activity embodies the stakeholder data analysis, stakeholder engagement, site visits, which includes funding agencies, policymakers, local communities, researchers, civil society and labor unions, schools and universities, and industries, co-creation technical workshops, international conferences, and the final commercial exploitation event, where we exhibit the technologies that we developed, and we have a workshop particularly dedicated to that, to exploit, find out commercialization opportunities, policy beliefs, articles in peer journals, standard and conference presentations, and newsletter kits, collaboration with other CCUS projects, very important. There are several projects which are going on at the moment, which are looking at CCUS clusters, website development, and social media channels and other media outreach. Many of these activities go on at the same time. So the fact that I'm clicking on each one of them doesn't mean that they appear consecutively. Several of them take place at the same time. And here is a distribution of the workload. So that's it. I stop here. Any questions?
Okay.
And in case you're wondering about this picture, am I allowed to explain, John?
Yeah, well, I think you better actually, yes.
Okay, this is what you get bored during COVID times. So I thought of a competition between our colleagues at UCL, a fruit face competition, basically, where people could basically make shapes of different things from fruits. So we had the fruit face competition, and this is one of them, the winning one.
Oh, very good.
Okay, so I thought it was something which pretty amusing and engaged a lot of people. We had a very good uptake, actually, something that you guys could also try at universities.
Yeah, well, I don't say that'll be the main takeaway from this lecture, but it could be significant nonetheless. Well, we're running on. Anything else you want to say, Paul or Haroun?
Oh, well, I think it's... Thank you, Paul, and thank you for your attention. Of course, this is there are several aspects to this project, and what the message which I hope I put across is that you need to, it's a holistic approach. You can't just focus on a particular aspect of the CCS without considering its impact on the rest. So any project to do with CCS, you need to look at the entire chain, and not just the technology, of course, the business aspects, but also the societal readiness. And I'd like also to thank the team, the C4U team. I'm just presenting their work. The hard work is done by everyone else. So in particular, my team at UCL also, who've been very helpful. Everybody has been pulling together. And so it's a very interesting and enjoyable project to work on. I've learned a lot from it.
Okay.
Thank you for the opportunity.
Well, and thanks to both of you for coming on and giving us such an interesting talk. Okay, right. Karis, anything else you want to say?
I think Vic is probably.
Oh, Vic, sorry, yeah, sorry.
Sorry, I was a bit confused whether
Yeah, sorry. I was
then. Sorry. Yeah, no, I'd just like to say a very big thank you to Haroun and Paul for giving your presentation very in depth and very interesting. Thank you very much both for coming. Next week we've got some flexible funded research updates from Professor Junwan Tang at UCL, which is on carbon dioxide conversion to high value chemicals by photocatalysis at ambient conditions, and also the monitoring of CO2 flow under CCS conditions, and that is with Yong Yan from the University of Kent. So 2 updates next week. So we hope to see some of you same time next week. But yeah, once again, thank you very much everybody for coming, and thanks for the talk.
Okay, see you everyone.
Take care.
Thank you.
Bye everybody.
Thank you.
Bye-bye.
Bye. Bye.